which is a continuation of the alkyne reactions that are pretty much the end of exam 3. The link to this video is going to be posted on Canvas and it's going to be on YouTube. All right, so let's start with number 1. Draw the relevant transition state for the following reaction and keep in mind that partial bonds are depicted as dashes. So over here we have a characteristic alkyne, more specifically a terminal alkyne, and we're reacting with this disec isoamyl borane reagent. So if you recall that this is very similar to hydroboration of alkenes, so what we want to do with this transition state is draw this trigonal planar molecule so that the disec isoamyl portions are farther away from the more sterically hindered side, or where all those substituents are, which is over here. Remember that this occurs via syn addition, so the isoamyl portions are going to add to this side of the alkyne triple bond, while this hydrogen is going to also add to the left side of this alkyne triple bond. So that's why these bonds are dashes. Simultaneously, this bond in between the hydrogen and boron is going to break because, remember, we're adding these via syn addition. And this terminal triple bond is going to go away because that's what happens in the structure. All right, so moving on to predict the products. So remember that when we're doing these characteristic alkyne reactions, we're actually forming something called an enol. And an enol is basically just the words alkene plus alcohol together. And enols readily tautomerize into ketones. So that's why you're going to see these carbonyl functional groups in your end product. So they're either ketones or they're aldehydes. So in questions 2 and 3, we're doing a very characteristic acid-catalyzed hydration of alkynes. So remember, we're thinking that we're going to put these enols on the more substituted side, and then that's going to readily tautomerize into a ketone. So if you look at number 2, we have 2 positions that we can think about in terms of regioselectivity. We can either put it on this secondary carbon or we can put it on this primary carbon. Clearly we want to put it on the secondary carbon. That's what this enol looks like over here. But that's going to readily tautomerize into a ketone, which is this structure over here. The reason we do this is because a carbon-oxygen double bond is a lot stronger than the carbon-oxygen single bond of this enol. So that's why this is a preferred structure. So number 3, we actually have a mixture of products. We have this ketone at the 3rd carbon, and we have this ketone at the 4th carbon. And the reason we have a mixture of products is there's no difference in regioselectivity in this alkyne triple bond. You have a secondary carbon here and another secondary carbon here. So we would expect to form an enol at carbon number 3, which tautomerize into a ketone on carbon number 3. And likewise, you're going to get an enol on carbon number 4, which tautomerizes into a ketone on carbon number 4. Hope that makes sense. All right, so for 4 and 5, we're doing hydroboration reactions. So again, we're going to be forming an enol on the less substituted or less sterically hindered portions of the alkyne. So when we look at number 4 or we look at number 5, we have a secondary carbon here and we have a primary carbon here. So clearly we're going to want to form the enol at that position, which will tautomerize into an aldehyde, because remember, it's at the end of a molecule, so it's going to be an aldehyde functional group. When we look at number 5, we have a secondary carbon here, and we also have another secondary carbon here. So there is no difference in regioselectivity, so you would also expect a mixture of products. So on carbon number 1, 2, 3, we'd expect that enol, and on carbon number 1, 2, 3, 4, we'd also expect that enol to tautomerize into 2 ketones. All right? Hope that makes sense. Let's continue with the reductions of alkynes. So for number 6, 7, and 8, all we're doing is varying the hydrogenation reagents, and this is very important for synthesis because we can actually manipulate our end products to get a certain product at the end. So let's say I wanted to form like a Z-alkene versus an E-alkene. I can use that in a synthesis problem to form a syndiol or something like that. All right, so in number 6, we have hydrogen and nickel, and this is that metal catalyst. It could be platinum or palladium, and it's going to take this alkyne all the way to an alkane, okay? So whether I have an alkyne or an alkene, or even both, this structure is going to go all the way to the alkane. Whenever we have hydrogen, nickel, platinum, or palladium, that's what's going to happen. In number 7, we're using hydrogen and something called a Lindlar's catalyst, and what happens is we're not going to go all the way to the alkane, but we're going to stop at a Z-alkene. So recall that we know that it's a Z-alkene because we have the highest priority substituents coming off of that double bond on the same phase. So if I put this line through here, I have a ring over here, and I have that isopropyl group over here. So that's why it's a Z-alkene. For number 8, we have pure sodium dissolved in ammonia. So what happens is that these alkynes are going to convert into E-alkenes. So we know it's an E-alkene because if I put that imaginary line through here, I have my highest priority ring over here and that highest priority methyl group over here. They're on the opposite faces, so they are E-alkenes. So just be cognizant of these in synthesis. We can manipulate our choice of reagents to form different types of end products, either all the way to an alkane, a Z-alkene, or an E-alkene. Be very cognizant of that. Something you might see on your test is a fill in the missing blanks section. So be cognizant of being able to interconvert between all these different structures. So for number 9, we go from an alkyne to a Z-alkene. We just talked about that, so that's going to be hydrogen and Lindlar's catalyst. Okay, so that's pretty much how we do that. And I'll just skip to number 11 for right now. If I'm going to go from an alkyne to an E-alkene, I'm going to want to use pure sodium and ammonia. Okay, so we did talk about that above. Number 10 is a little bit difficult. So we see that we have a mixture of products. We have this ketone functional group on carbon number 4 and this ketone functional group on number 3. So we're thinking that we started with some sort of alkyne to begin with, and more specifically, there must not have been a difference in regioselectivity because that's why we have 2 different products. So what I can do is I can just basically form that alkyne triple bond in between the carbons of where this carbonyl groups are. So I would expect an alkyne in between carbons 3 and 4. So 1, 2, 3, and 4. That's why this functional group is right there. All right, finally, the last problem, we're on organic synthesis. I know it's not everybody's favorite, but I can give you a couple of tips to get through these. So the first thing I would do is count the number of carbons. So for number 12, I see this alkyne, and it's going to be a 2-carbon alkyne. And all the way to the right, I see a very long carbon chain. And more specifically, I see I added some hydroxyl functional groups. So we should immediately think to do acetylide addition. That's the first thing I would do. So step 1 of this reaction is going to deprotonate that terminal hydrogen, and it can form an acetylide anion that's going to nucleophilically attack this partially positive carbon due to its proximity to that chlorine, and that's going to extend the carbon chain on the right side. But notice on the left side of this molecule, I also have another methyl group. So in order to do that, I can do another acetylide addition with step 1 over here, deprotonating that terminal hydrogen on this alkyne, and then doing a nucleophilic addition reaction to this haloalkane. And that's what this end product is. So now once I got to this structure where I added my carbons, I need to figure out how I added those 2 hydroxyl groups. Well, these 2 hydroxyl groups are 1 carbon apart, and they're also on the same face, okay? So if I rotated this up, I would see that these are on the same face, which is syn addition. So I'm thinking I added osmium tetroxide in some sort of way. So to go from this alkyne to the right alkene, I'm going to use H2 and Lindlar. And there's a reason why I chose this and not sodium and ammonia, because this Z-alkene is what is the proper conformation for osmium tetroxide to do that syn addition to form that syn diol, okay? So you have to go to this Z-alkene to add that syn diol, and the only way that I got from this structure to that final structure is rotating this carbon-carbon bond back down. All right, I hope that makes sense. If you have any questions, email me, and good luck studying this weekend.